Okay, so last time we introduced a few concepts. One was the concept of integration, which is in some way the opposite of differentiation. We introduced the concept of seasonal integration, and so seasonal differentiation. We show that actually we can represent the operation by using some abstract operators, which even if you see them for the first time, you know already how they work because they obey the same algebra as like complex variables, okay? We saw a little bit the cum-sum function and the filter function of R, which are good for example, simulating sample path of these processes, because as you now know, in statistics, usually we want to produce a data generating process, a probabilistic data generating process that seems to generate data that are close to the one we want to model, and then use those models to estimate the unknown parameters, and then use those models to, in this case, predict, okay? Which is a slightly different approach than when you go with some machine learning models. Then we introduce, okay, the random walk with drift. Okay, it's an integrated process, but this is something we have to learn to cope with. In integration, if I have like a mean zero variable, I have a purely non-deterministic trend. We can call it trend because it's non-stationary. But if we have some kind of drift, which is the thing here called beta, then that actually turns out to be a deterministic trend, because we showed that such a process, whatever epsilon is, in this case, it's just a white noise. But even if it's a stationary process with mean zero, then I'm accumulating the stationary process and I get an integrated process. But if I have this drift here, I also get a straight line, so like a very deterministic trend. So it's the sum of, or let's say, a deterministic trend and in some way a stochastic trend. We call it stochastic trend because it's non-stationary, and as we mentioned, okay, we can theoretically define the mean, but actually the mean is not well defined. So if the process doesn't have a mean, probably we can call it a trend. But anyway, this is the sum of a deterministic function and a stochastic process, a non-stationary stochastic process. Then we introduce the autocovariance function, which in some way we already saw in the definition of a stationary process. We saw that in general, the autocovariance function is a function of two time indexes, because of course it depends on what is the observation yt and when is the observation ys. And for example, for the random walk, we computed that. Actually, no, I left that as an exercise, so you should have tried to demonstrate, to prove this. So the autocovariance between a process at time t and time s is just the minimum of the index over the time index multiplied by the variance of the white noise that drives the process, okay? But for stationary processes, we said actually it doesn't matter when we compute the covariance. So it doesn't really matter when I compute it between t and s, because it's time independent. So it's just dependent on how far away in time are the observation t and the observation at time s, okay? So actually, in a stationary process, everything depends, the covariance depend, the autocovariance depend only by the distance between two time points, but not the time we are computing that. And so for stationary process, the autocovariance function is just a function of one parameter h, which is just the lag between the two observations we want to compute the autocovariance between, okay? And so this allows us also to compute estimates of the autocovariance function using just the sample covariance, okay, with a small change that we are not dividing actually by the number of observations we are summing, actually we should divide by the number of observations we are summing minus 1, because 1 is for the estimated mean. But in this framework, we prefer just to divide by the same n all the autocovariances, because in this way we preserve the property of positive definiteness of the covariance matrix, which is in this case the autocovariance matrix. We can call it this way, we can build it this way. Okay. And of course, we can compute the so-called autocorrelation function, which is just a transformation of the autocovariance. I just have to take the autocovariance at time h, at log h, and divide by the variance. In that case, I get the autocorrelation, which is of course a number which is between minus 1 and 1, and tells us how much linear memory a process has of its own pairs. Of course, autocovariance and autocorrelation are a symmetric function of h, so the log. You can prove that. Right? It's very simple to prove it, just because it's stationary, so it's time independent, and because the covariance function is symmetric in its two arguments. Okay. So the next thing we were going to do is introducing some models for stationary processes. But before doing that, I wanted to show you something. Actually, if we know the mean and the autocovariance of a process, we can carry out linear prediction without further ado, because it's all we needed to do. You know, if you remember linear prediction, for linear prediction, all we needed to know is the first two moments, so the mean and the covariances in some way. Okay, so if we have the autocovariance function of a process, and of course its mean, then we can already predict the process linearly, and just by applying the formula we saw a couple of lessons ago. So, for example, let's do this theoretical exercise, which at the moment is theoretical, but then it will become very practical. Suppose we have a time series it can be also, I don't know, very short, like just 5 observations, okay? And we want to predict the sixth observation, and assume that yt is generated by a stationary process, and we know the mean of the process, so we can call it mu. It's the mean of the process, which is of course time independent because it's a stationary process. And suppose that we also know the covariance function, which we can call gamma of h, because it's a stationary process. So the autocovariance just depends on how far away are the observation. So let's try to just theoretically apply the linear predictor. This is all we know to apply it. So let's try just as a simple exercise to do that. So we want to predict the sixth observation. So we want to do the linear prediction of the sixth time, whatever, of this time series. And we know all of the other one from number 5 to number 1. Okay, well, we just need to take this formula. I told you this is one of the few formulas a statistician, a data scientist should know by heart. But anyway, we have like the mean of y6, which is, it's a stationary process, so we know the mean. We call it mu of y, because it's all the same. Then we need the covariance of y6 with all the other 5 observations, but we know that because that's just the autocovariance function at log 1, at log 2, and so on. So I'll just write it very let's say expanded as much as I can, so it's all clear for you what we're doing here. So this is the covariance between this observation and all the other 5 ones. So this is going to be like a well, this is going to be a row vector, and we have y5 minus the mean. Then we have y4 minus its mean, and so on up to y1 minus its mean, okay? So this is just what we call sigma yx, because here our x vector is this, okay? And y is just this y6, okay? So this is the covariance, which we can now, you see it's just the covariance between the 6th and the 5th, which is just a log 1 difference. So this would be gamma 1. And then we have the covariance between gamma 6 and gamma 4, which is a log 2. So it's autocovariance at log 2. So this vector here is actually equal to gamma 1, so this with this one. Then we have gamma 2, because it's this one with this one, it's 2 logs, okay? Up to 5 logs, because the difference between y6 and y1 is just 5 logs. And so we have these covariances. Then what we have here, if you remember, we have to multiply this time the variance of the vector x, but the variance of the vector, the matrix, the covariance matrix of the vector x is just the autocovariance matrix in this case, because I have to take, of course, the autocovariance of y5 with y4 and all the other variables. So actually, this is just the inverse, of course, of the covariance matrix of the x vector, and in this case, the x vector is y5, y4, up to y1. And so this is just the autocovariance of dimension 5, which is going to be gamma 0 on the diagonal. And then we have gamma 1. This is up to gamma 4. Here's up to gamma 4, and so on. So here would be gamma 1. So it's just a symmetric autocovariance matrix, okay? And we have to invert that, of course. This is also called Toeplitz matrix, this kind of matrix where you have like the same objects on the diagonals here. So the main diagonal is the variance, and then the diagonal over the main diagonal and below the main diagonal is just the same again. Gamma 1 and so on. These kind of matrices, they're called Toeplitz matrices, and they have some special properties also to do computation. They're kind of numerically simpler to treat. And then finally, we have, of course, the vector of the y5, y4, up to y1, minus the mean, which is the same for all of them because it's stationary, okay? So why did I show you this? Well, I show you this to convince you that if we know the mean and the autocovariance function of a process, we are ready to produce prediction without further ado. We don't need anything more. Of course, linear prediction. This is the linear predictor, okay? So this would be like, if we want to just write the formula, would be like this. Okay. So this is 1 times 5. This is 5 times 5, and this is 5 times 1, okay? So everything is clear. So in some way, I want to do linear predictions of a time series, what do I have to do? I have to be able to estimate the autocovariance function, the mean, of course, and the autocovariance function of that process. The problem is that, of course, if I have a very long time series, suppose like I have 1,000 of observation and I want to predict the 1,001th observation, 1,001st observation, then this matrix become huge. Okay. Of course, if it's a known matrix, it doesn't really matter. We can try to find a way algorithmically to treat that. But the problem is that how can I estimate so many covariances? I mean, if I have 1,000 observations, it's a lot of observation, but if I have to estimate 1,000 covariances, then it's not a lot of observation. It's too little observation. So in some way, you can, starting from now, you can see linear models for time series as parsimonious ways to let these big covariance matrices depend only on few parameters, okay? So a way to, like, instead of making, like, if we had like 1,000 past observations, this would be 1,000 times 1,000, and this would be 1 times 1,000, which is a lot of things to estimate. If we can make this function, this autocovariance function, just depend on few parameters that we can estimate on the observations, then we solve in some way a problem. So as I told you, linear time series models are just models to, you can see it this way, you can see it in many ways, but you can see it just as a way to build autocovariance functions that fit the data and depend on a number of parameters which is small. So it's parsimonious model that can fit also very large time series. And of course, as we already saw, real-time series are usually non-stationary, but we saw that the non-stationary parts in some way we can treat by transformations that can then be anti-transformed. So we can get back on the transformation. So we saw the log, or even larger class, the Cox transformation to deal with non-stationarity invariance. And then we saw the differences of two kinds, so seasonal and non-seasonal. We can deal with like non-stationarity mean and also seasonalities, which is also a form of non-stationarity mean. So, okay, and so this is if we solve that problem there, then we also can just rely on stationary models, because all those transformations we can reverse, and so we can just predict stationary process. And so now we start learning a class of models that maybe some of you already encountered. So these so-called ARMA processes that are very good at modeling stationary processes, and so build a parsimonious parameterization of this covariance matrix. Okay. Of course, this thing here is not only true for stationary processes. You can try to do a couple of exercises. There are many exams. I think the first exercise, many exams, is just an exercise about linear prediction or prediction in general. Okay. Of course, you can also try to predict like a random walk, or, for example, I mean, predicting a random walk is very simple, but if you want to use the formula of linear prediction, that this becomes a little bit more tricky. But for example, take a random walk. Let's start, okay, let's make it start from 0, and then you take a random walk. Well, this is a white noise with this variance. And I don't know, we already saw that the covariance between yt and ys is just the mean between t and s times the variance of the white noise. Then we know the mean. Well, the mean is 0. The mean is the first value, so the mean of this random walk would be 0. and the covariance is this function. Well, then you can, for example, if you want to predict like a future observation, I don't know, n+5, and you just know, for example, the last two observations, try to solve that, okay? In some way, we can already expect what's the solution of this, because it's a random walk. In a random walk, all the information is contained in the last observation, because of course, future observation are just the last observation plus some white noise, the sum of white noises. So we can already expect that the expectation of a future observation is just the last observation, which is the characteristic of a white noise. But if you apply the formula of linear prediction, then you should come to the same results in a more involved way in that case. In that case, it's much simpler to compute the conditional expectation, exploiting the independence between this, but the conditional dependence of the past given the future. But of course, you can apply, I gave you the mean, I gave you the covariance function of a random walk, so you can write down, do the computations and see that actually the prediction of yn+5 is just yn, but you can prove it in a more difficult way than just applying the formula. Just an exercise, but try to do. Because of course this formula works for whatever process you have, okay? Not just for stationary process. Good. So let's start with the so-called autoregressive processes. Some of you, when I asked in the first lesson, what do you suggest as a model, a simple model, to predict a future of one time series given its past? Some of you said, well, I would regress the time series on its own path. And that's basically what are autoregressive processes. So let's define the autoregressive processes. Usually, you put it this way, and you see P is the order of the autoregressive process. Let's start with just processes without an intercept, and then we will add the intercept. Anyway, it's just a process where the observation of today is a linear combination of the last P observations, okay, plus a white noise. Okay. Of course, it looks like a regression. You have to think in two different ways. One thing is the definition of a process. So this is the data generating process in some way. And the regression is usually the instrument we use to try to fit this to data. Okay. So this is, at the moment, you see it as a way data are generated from. As I told you, in statistics, usually we want to produce a probabilistic model and use data to estimate what we don't know of that probabilistic model. In this case, what we don't know of this probabilistic model is the fees, so these coefficients. And of course, I can assume some distribution for the white noise, for example, the Gaussian white noise. In that case, I just don't know the variance of the white noise. I could define Y to be a white noise of different distributions class. Students T or Cauchy or whatever you want to use. In that case, the number of parameters to estimate could be more than just the variance, because some other distribution may have some shape, parameters, and so on. Of course, usually the Gaussian distribution is the one which is assumed. Doesn't have to be, okay? And again, this is just the white noise. With variance sigma square, okay? What are the properties of this model? In some way, I told you that ARMA models, of which are processes are just a special case. We use them for the stationary part of the time series. We cure the non-stationarity of the process, and then we start analyzing the stationary, what's left after transformation, which is stationary. Well, an autoregressive process doesn't have to be stationary, actually. You see it straight away. Take an autoregressive process of order 1 and set the phi coefficient equal to 1, you get the random walk. So it's simple to say that actually an autoregressive process doesn't have to be a stationary process. Okay, actually it can be stationary, it can be integrated. What does it integrated mean? That if I take one or more differences, I can make it stationary, even if it's the original process is not stationary, but it can be even explosive. What does explosive mean? Means that the process quickly go beyond any fixed number. Explosive processes are usually rarely useful on real data because, of course, an explosive process could exist, but just for a short time, because after a while it explodes, okay? So, for example, an explosive process could be like a financial bubble. You know what a financial bubble is? When, for example, the price of a stock just increases like crazy, and then, of course, the bubble explodes, and so the explosive process can only last for a given time. It can last forever. If it lasts forever, it goes to infinity very quickly. Okay. But otherwise, it's really rare to find useful application of an explosive process. So it's more interesting to have either stationary processes or integrated processes, which we know how to make stationary. So I'll give you a couple of rules to understand when an autoregressive process is stationary, and then I'll tell you why we need to reason about taking a difference or not before analyzing the process with the autoregressive model. So, let's start. A very simple example is the AR1 process. Okay. So from this toy, actually it's useful. It's not only a toy example. As I told you, we can see straight away that if phi is equal to 1, then we have the random walk, and so we can also generate non-stationary or actually integrated processes. Okay. In this case, I can show you that if phi is in modulus strictly smaller than 1, then the process is stationary. And if phi is instead larger than 1, it's explosive. So this is useful, this is useful, this is rarely useful in real-time series analysis. In some way, we can, for example, derive what's the mean of this process and what's, for example, the variance, maybe the autocovariance. Let's try to do this. Let's try to compute the mean. First, assume that phi is more than 1. Why do I assume that? Well, I told you we could prove that. I told you this. In this case, the process is stationary, so a mean exists, and a time invariant mean exists. A variance exists, and an autocovariant function exists. Okay. So I told you if this holds, then we have a stationary process. So there is a mean that we can compute. So that's just to show you how we can derive the properties of some of these processes. So if I want to compute the mean, well, the mean of y, of course, is equal to the mean of phi yt minus 1 plus the white noise, right? I just took the expectation of the left side hand side and of the right hand side of the equation, right? So this is the mean, and we can call it mu, okay? Then we have phi, which is just a coefficient which can go out of the expectation. And then we have again yt minus 1. Well, this is a stationary process, so this is also equal to mu, okay? And then we have the expectation of a white noise, which is 0. So what is mu? This has to hold whatever the phi is if phi is in between minus 1 and 1. So what's the solution of this equation here? 0. So the mean is 0. This is equal only if mu is equal to 0, okay? I took the expectation left on the left on the side. It comes out this equation that the mean, this is the mean because we took the mean. This is also the mean because it's stationary. I told you when phi is in modulus less than 1, the process is stationary. So the mean of yt is equal to the mean of yt minus 1, okay? So I write mu. This is just phi. It goes out of the expectation. It's a coefficient, and it's not a random variable. And then we have the expectation of the white noise, which again is 0. And so we have this equation for the mean. And of course, the only solution of this equation for mu is because it has to hold for any value of psi is 0. So the autoregressive process in general, if there is no intercept in the model, is 0 of a stationary autoregressive process. So the mean of an autoregressive process without intercept is 0. It tends to, we will simulate from them, but it tends to oscillate around 0, okay? Let's try to get the variance, for example. So we do the same thing. We take the variance of the left-hand side and of the right-hand side. So the variance of yt, or maybe even better than that, let's take, since the mean is 0, we can take the expectation of the square. And then we take the expectation of the square of the right-hand side. Well, if you look at this way, okay? So we can call this, well, gamma 0. Now we call the variance of the process gamma 0, so we can call it this way. Here what we have, well, we have the expectation of phi square yt minus 1 square plus yt square, and then we have the cross product, the double log cross product of yt minus 1 and yt. Now, well, this is linear, so, well, phi square can get out of the expectation because it's just a coefficient. So we have the expectation of the square of the process, which is, again, the variance of the process, comma 0. Then we have the variance of the white noise, which we call that sigma square. And then we have, in practice, the 2 phi, the covariance between yt minus 1 and epsilon t. But, so this is a white noise. So, well, this depends on just past the white noise. Actually, I could write this as a infinite sum of past white noise. So this is actually uncorrelated with this. Okay, so this is 0. And so we have that the variance has to respect this equation. So if we solve for the variance of the process, we get sigma squared divided by 1 minus phi to the second power. So this is the variance of an AR1 process, which is, of course, it depends both on the variance of the white noise. Of course, the larger the white noise, the more also Y goes up and down. But it also depends on the value of phi. If phi is very close to 0, then we have a process which is very similar to a white noise, and then the variance will be close to the one of the white noise. If the phi, which in moduli has to be smaller than 1, because otherwise it's non-stationary. But if phi goes closer to 1 or minus 1, whatever you want, then you see that the variance increases. And actually, if we take the limit for phi goes to 1, so phi goes to 1 means the process gets closer and closer to a non-stationary process, then we get an infinite variance. Indeed, a non-stationary process, if we cannot assume that it was born in infinite past. Otherwise, the variance would be infinitely large. We saw, for example, the random walk, the variance increases with t. So if we start with a given observation and then we move on, the variance grows with t. But here we are not assuming any starting point, because we can do that in a stationary process, because in a stationary process, things don't change. So I can assume it was born in the infinite past. That thing I cannot assume when I have a non-stationary process, okay? Or an integrated process. So this is just to show you how we can derive the theoretical moments. And of course, we could also derive the autocovariance function. I mean, I will do this only for the AR1 because it's simple, while it's much more involved for a general ARP process. But at least once I wanted to show how to derive some properties of these processes, okay? Because I think it's important to know how to handle them. So let's try to compute, for example, the lag1 autocovariance. So what we call gamma 1, which would be yt times yt minus 1 under expectation. Because we saw it's mean 0, so the autocovariance is just the expectation of the product. For example, we could write, instead of writing yt, we could use the definition of yt and say, okay, this is equal to the expectation of phi that multiply yt minus 1 plus the white noise. Okay, this is just yt. It's the definition here. I'm just using, instead of yt, I have just written the definition of the process, okay? Which is stationary, okay? Yep. And then we have t minus 1 here, okay? So what happens? We get, again, we do the product and take the expectation. Here we have phi times the square of yt minus 1 under expectation. So it would be phi, which is just the coefficient, and then we have the expectation of yt minus 1 squared, okay? And then we have plus, again, phi can get out of the expectation because it's not a random variable. And then we have, no, phi doesn't, we don't have a phi, sorry. It's epsilon times yt minus 1, okay? Again, this is in the future with respect to the process, so this is not correlated with this one, so this is 0. And so we have actually that gamma 1 is just 5 times, this is just gamma 0. This is just the variance of the process, right? And in general, actually, you can prove that gamma h is just phi times h minus 1. In some way, you kind of see that the autoregressive process also works for the autocovariance function. Yeah, of course, we will have plus something here. This holds, of course, for h from 1 on. Okay. So we know how to compute the variance. We already saw it there. We can compute all the other covariances this way, or which is equivalent also equal to okay. So the autocovariance function of it's very simple to write down the autocovariance function of a AR1 process because it's just we can usually we plotted we saw already last time in R we computed the sample autocovariance function of a couple of time series. So this would be the autocovariance function or autocorrelation function, whatever. Now, of course, what about the autocorrelation function? Well, we just have to divide the autocovariance function by gamma 0. So the autocorrelation function would be just equal to 5 at the power of h. And then we have gamma 0 divided gamma 0. So this is it. Okay. So in some way, so if this, well, for some reason I told you, which is not intelligent, the ACF function of R computes also the autocorrelation for 0 lag, which by definition is 1. But then suppose that phi is 0.9, then here we have, this is the first lag, this is 0.9 at the second power, so it would be, sorry, this is the first power, so it's 0.9. Then we have the second power of 0.5, which is 0.81, and so on, okay? And so you will notice that the autocovariance function of a stationary process in some way goes to 0 in a geometric fast way or exponential fast way, okay? So the autocovariance function of AR1 processes just looks like this, okay? Of course, if phi is negative, it bounces because it changes sign every time because like odd powers are positive and are negative, so sorry, and even powers become positive, right? So if phi is negative, then it bounces up and down, but it goes to 0 at an exponential power or geometric power, okay? Why am I showing you that? Because usually we will do the opposite process. So we will look, first we make a time series look as stationary as possible, then we look at the autocovariance function or autocorrelation function and try to understand which process is able to generate that kind of autocovariance functions, okay? So we will learn how ARP and MAQ processes produce, what kind of autocovariant functions they produce. That's why we need, we don't need to compute for them I will give you some rules. We just compute this once for the AR1 because it's simple. It's more involved if we have a general ARP process, but anyway, it tends to work in similar way. Of course, if we have a more complex ARP process, we will see that actually the autocovariance function, if it's stationary, it goes to 0. This is in some way, at the moment, maybe to you, it doesn't sound so immediate, but in some way, for a process to be stationary, in some way, it has to forget what happened in the past, sooner or later, because if a shock enters forever in the system, then it changes forever the system, so it cannot be stationary. So any stationary process, in some way, from in an intuitive point of view, has to forget what happened a lot of time ago. So all shocks have to be forgotten sooner or later. And in some way, this corresponds to an autocovariant function that goes to 0. It goes actually quickly enough to 0. In this case, it goes to 0 in an exponential fast way, okay? So the memory of an autoregressive process is there. It can be also very long, but eventually it goes to zero, okay? In general, so if we have a, so we said most of it, okay, we can add one thing to the AR1 and then move to the more general process. This is a mean zero process. Again, maybe it's not that useful for real data. Real data, they don't have to be mean zero. How can we generate a process with mean which is different than zero? Well, the simplest thing is we just add a mean to the y. So we define a new process which is yt plus mu, and so we have a mean whatever process. But otherwise, we can put an intercept in this equation. So let's try to put an intercept, which we can call k. Okay, let's compute again the mean of the process. So we started by saying, okay, we can take the expectation left and right. Well, the expectation is linear, so we have the expectation of k, but k is just a coefficient, so this is just k. Then we have the expectation of phi times yt minus 1, but again, phi is just a coefficient, so we have the expectation of yt minus 1, and then we have the expectation of the white noise. But sometimes I use the parentheses, sometimes I don't, whatever you want. Because you can see the expectation as an operator, and usually for operators, you don't apply parentheses, or as a function, in that case, you apply the parentheses, whatever. Anyway, so we have, this is the mean. We are still assuming stationarity. So for assuming stationarity, the phi has to be in modulus less than 1. So if we assume stationarity, well, this mean has to be equal to this mean. And of course, the mean of the white noise is 0. So we get an equation where we have mu is equal to k plus 5 times mu. This time, 0 is not the solution. We can solve for mu. And solving for mu, we see that we get k divided by 1 minus 1. Okay? I'll just solve this equation for mu. So the intercept is not the mean, but it's tied to the mean in some way, okay? So if there is no intercept, if the intercept is 0, as we already seen, we have 0 mean, right? But if the intercept is non-zero, then we have also a proportional mean. So a mean which is proportional to the intercept, and it's just given by the intercept divided by 1 minus the AR1 coefficient, right? Okay, so we have like now a stationary AR1 process. Now let's just without proving the things for the general ARP process because it's cumbersome, let's generalize all this information I already gave you for the AR1 to the general ARP process, which is the process which is more useful for real applications. So, so the AR1 or ARP process with intercept, we can write it this way. Okay, first of all, I show you a different way to write this equation, which you will find most of the time in the literature, and it's also useful then to understand when the process is stationary and when it's not. So remember we defined a few lessons ago the backward operator, or which is also called the lag operator if you go into the econometrics literature, or delay operators if you go into the engineering literature, whatever. So the backward shift operator, by exploiting this operator, we can actually write this process as one, or identity, whatever you want to call it, minus phi 1 times b minus phi 2 times b squared, and so on, times yt Can you see why this is just the same thing written a different way? Of course, if you multiply, this is an operator, so a polynomial operator. So it always has to be on the left side of yt of the process, okay? If you put it on the right-hand side, it doesn't have any meaning because this applies to yt, okay? But anyway, it's an operator. So if you multiply this operator times the process, you get yt minus phi 1 times yt minus 1, and so on. So you get on the left-hand side yt minus all these yt's here, okay? And of course, the power here means how many logs of the yt process you are taking. Is that right? Are you following? It's just a different way to write this. Why is this important? Well, this is important for many ways. In some way, it's also important because usually you make it even shorter. You can see this as a polynomial in some way. It's a polynomial in the B operator, right? This is just a P order polynomial, right? And so usually you write it even shorter than this. You write it usually just like this. Where this is just a polynomial of order P. Instead of being a polynomial in a variable, in an X variable, whatever, it's a polynomial in the B operator. But as I told you, you already know how to handle it because it's the same algebra as that you know already. Okay. Good. So why is this polynomial so important? Because if the process is stationary or non-stationary, it depends on the solution of this p-degree equation. So if instead of using b, I use a general, I don't know, ax or zeta, whatever you want. Let's say zeta because the solution can also be complex. So if we take this this equation, 1 minus phi 1 zeta minus phi 2 zeta squared, etc., y phi p zeta p power equal to 0. So if I equate this polynomial to 0, of course I have a p-degree equation that by definition of by the fundamental theorem of algebra, it's got p solution, right? The p solution, they don't have to be all real. Some can be real, some can be complex or complex or whatever. But there are p solutions, right? And the rule now is that the autoregressive process that has this polynomial, sometimes called the characteristic polynomial of the AARP process, if all the roots, so all the solutions of this equation are all, usually you say outside the unit circle, meaning larger than 1 in absolute value or in modulus. The absolute value in a complex number is the distance from the center. We can see. We can review a little bit of complex numbers if you don't know much about complex number. But anyway, if all the solutions of this equation, so the p solution, they all have modulus which is greater than 1, then the process, the ARP process, is stationary. Okay? Okay. To see why this works also for, I mean, we did actually I told you that for the AR1 process, the only phi that we have in the case of the AR1 process, that phi had to be smaller than 1 in modulus. Okay, let's see if it's actually a special case of this. So, so the equation is just this one, because it's just an order 1 polynomial. So we have zeta. So the solution is just zeta is 1 over phi, or phi, whatever. If this has to be larger in modulus than 1, so implies, or it is implied by, phi smaller than 1. Okay. So this zeta is larger than 1 or smaller than -1 if phi is between -1 and 1, right? So actually what I told you about the AR1 comes out to be just a special case of this general rule that I gave you for the ARP process, right? Is it clear what we're doing? So I gave you a machine to generate data, which is called ARP, and we are studying the behavior of this machine. We saw that it can produce a mean, which is not 0 if we have an intercept. It produces memory. It produces some autocorrelation function. We saw that for the AR1. Of course, this produces autocorrelation functions which are more flexible, more, can have different behaviors, but they all, if the process is stationary, all the autocorrelation functions will go to 0 eventually. Very slowly at the infinity, but eventually at the infinity they will be 0. Okay, and we saw when stationarity happens. Okay, but actually we saw also in the case of AR1 processes that also integration in some way is contained into these processes, because we saw the AR1, if I set phi equal to 1, I get the random walk. The random walk is non-stationary, but the difference over the random walk is stationary. Okay, so in some way, integrated processes are also special cases of autoregressive process, and this comes when you have at least one solution, or root, as you want to say it, that is equal to 1. So of course, if one of the solution is equal to 1, or even more than one of the solution, then you're not outside of the unit circle, so it's non-stationary. But if we have one root which is equal to 1, then we have a non-stationary process, but its difference is going to be stationary, and I'll show you why. So suppose we have the this polynomial in B. Okay. Suppose we have all the solutions of this polynomial. Okay. So we have the zeta 1, zeta 2, zeta 2. So we have the roots or solution, whatever you want. Of course, of the when I take the polynomial makes equal to 0. Then we did this, I think, in the high school. We can factorize a polynomial by multiplying monomials, right? You know, Ruffini, that kind of stuff. So, and I mean, you had to wait like 5 years to see that factorization of polynomials as actually one application in real life or real life. Well, this is application. So we're going to apply it here. We're going to apply it in a slightly different way, because this polynomial has some characteristic which starts with 1. Okay, it's different than the general polynomial starts also with the phi 0. Okay, in our case we have a 1, so we have a special polynomial, but the thing don't change much. So you can trust me that we can factorize this operator as such. So 1 minus sorry. Right. Okay, once I found all the solution of this p-degree equation, I can rewrite the polynomial as the product of monomials. And these are the roots, okay? So suppose one of these roots is equal to 1. It doesn't really matter which one. Let's suppose the last one is equal to 1. Good. Then what we have is just an operator. Suppose this is one of the solutions. So this is called unit root in some way, because it's a root, so a solution which is equal to 1. Then we have, well, this part here, which is unchanged. Okay. So the operator we can write this way, because, you know, zeta p is equal to 1, okay? So if I write, so this will be what? Well, this will be just another polynomial of p minus 1 order, and this is just the difference. No, this is the difference. So the process which I'm building is this process. If you see it, it means that yt is non-stationary. We know it's non-stationary because there's a one unit root solution, so it doesn't apply the definition of stationarity, or actually the property of stationarity. But what we see is that if I take the difference of yt, I get the rest of the polynomial, which I'm supposing all the other roots are outside the unit circle. So this is a stationary operator. This is the difference, and this is the time series. Okay, so actually, integrated processes are special cases of autoregressive processes, and there are cases of stationary autoregressive processes that have one solutions, one root equal to 1. Indeed, in the literature, you will see that integrated process or unit root process are synonymous. It's just the same thing. You will find out in the literature there are unit root tests. They are just tests to find out if a process is integrated or stationary. Okay, so integration and unit root are synonymous. if I have just one unit root, then, and all the other roots are outside the unit circle, so they are larger than 1 in modulus, then the process is I1, because there is just one. After one difference, I get just the stationary operator. But if I have two, for example, unit roots, then the process is I2, because I need, suppose that we have two. Then I can factorize the operator in this way. And the process can be written this way. So this is stationary operator, a stationary operator. These are the differences. So it means that if there are two unit roots, I need the two differences to make the process stationary. Okay. So there is a, as I told you, there is a binding between the concept of integrated processes and the autoregressive class of processes. Okay. One quick way to understand, suppose you estimate an autoregressive process on real data. And you want to check if there is some unit roots in your estimated error pre-process. Well, of course, you could use, for example, in R, there is the polyroot function that finds the solution on a polynomial equation. But otherwise, a simple trick to find out if a process that you estimated has a unit root, you just need to sum all the phi coefficients. If the sum of the phi coefficient is equal to 1, then there is a unit root in the process. Yeah, you can see it from the equation here. Suppose that 1 is a solution. This means that if instead of zeta you write 1, this is true, right? So it means that 1 minus the sum of all the coefficients is 0. Okay? So if 1 is a solution of the system, then the sum of the coefficients of the autoregressive coefficient is 1. Or, of course, if they are estimated, it's very close to 1. One thing, when we are going to estimate these processes, either by least square or maximum likelihood, what happens is that the estimates, they are distorted towards stationarity. So that's why usually we ask ourselves, is this process integrated and I have to take a difference, or is this process stationary? I ask myself before estimating an autoregressive process if there is some kind of non-stationarity, so integration in this case, because the estimates tend to be biased towards stationarity. So I will have a hard time to find non-stationarity by using a least square or maximalized square, maximalized loop. Okay, so that's why I have to ask myself, looking at the time series, looking maybe autocorrelation function, is this time series stationary or not? And I want to answer that question before moving to fitting an autoregressive process. For that reason, because fitting an autoregressive process will give you too often a stationary process, even when this process is non-stationary. Okay, we can play around now with R to kind of visualize all the things. These are theoretical things, but they have an immediate interpretation as far as how the data look like. Okay, is this all clear? Are there questions, things there? Of course, we will not look for the autocovariance function. which is, of course, can be very complicated. It can even be oscillatory in some way. If you have, if some of the solution of the characteristic equation are complex, so if you have complex solution, if then they're not all real, then you will find oscillations in the data. Okay. So the memory, which you see also in the autocorrelation function, will be sinusoidal in some way. Okay? So for example, if you want to build a model for a business cycle, talking about economics, a business cycle is something that goes up and down, of course in a stochastic way, but it goes up and down. So probably you need a process that has complex solution or complex rules. And in some way, you can also impose that in some way, but let's not give you too much information for now. Okay. What about the mean? Well, the mean is simple to compute, so we can compute it ourselves. So let's try to compute the mean of an ARP of a stationary ARP process. Well, of course, with intercept, otherwise the mean is 0. So let's take the expectation on the left-hand side and on the right-hand side of the process. So k plus phi1, the first delay of y, and so on up to phi p times yt minus p plus the white noise. Okay. So this is the mean. Then we have the expectation of k, which is k. Then we have the expectation of phi1, which is phi1, times the expectation of yt minus 1, which by stationarity is again mu. So we have phi1 times mu, and so on up to phi p times the expectation of yt minus p. Again, this is a stationary, so the mean doesn't change over time. And so we have mu, and then we have the expectation of the white noise, which is 0. Then let's solve this equation for mu, and we get that mu is equal to k divided by 1 minus all the coefficients phi. Okay, so this is how the autoregressive coefficients and the intercept are related to the mean of the time signal. Okay. Again, as I told you before, if there is a unit root, the sum of the phi coefficients is equal to 1. If this is equal to 1, this goes to infinity. Okay, so there is no mean, because a non-stationary process doesn't need to have a mean, of course. Okay, but a stationary process has a fixed mean. Okay, let's try to play around a little bit with this process just to see how they look like. In some way, we can expect, for example, when the sum of these coefficients is close to 1, it's not equal to 1, but it's maybe the sum of the y's is 0.98, then probably the process has a very long memory. It's not random walk. A random walk has an infinite memory, but it's going closer and closer to a random walk. So as far as the phi's, the sum of the phi's is closer to 1, then the longer the memory of the process, so the more persistent the process. When I already mentioned to you what persistence means, that, for example, if the process is above the mean, then it stays above the mean for a long time. And if it's below the mean, it stays below the mean for a long time. So this is a highly persistent process. Okay? So if this sum is close to 1, then we have, it's not 1, so we're still stationary. But if it's close to 1, then it's very persistent. And very persistent means very predictable, okay, in some way. Because it means it changes but slowly. And the white noise is not persistent. We cannot predict the white noise because it just changes every time. Okay? every time can be above or below the mean and close or far away from the mean and so on. Good, let's play around using simulating some of these processes. We have the famous filter function that we played around last time with. So let's start maybe with just an AR1 process. We can fix this would be the AR1 coefficient when we can fix the variance. The variance is not that important, it's just a scale factor. So let's just suppose the variance is 1. For example, let's generate an AR1 process by using filter, and of course the X in this case is the generator of white noise. We can generate, of course, Gaussian white noise, for example, or maybe I can also parameter. So the length of the time series. Then we have the filter, which is just, in this case, is just phi. And then we want the type of the filter, which, no, it's type, what was it? It's method, so sorry, method, not type. And it's, of course, it's recursive. Recursive means autoregressive. It's just the same thing. It's just synonymous. Maybe I can turn this into time series so we have a line plot. Okay. Of course, this is all random. So every time I generate a different process, but what we see, okay, here, for example, we didn't put any intercept. So these are all mean zero processes, okay? If I add an intercept, so k, for example, equal to 1, then I have to add it here, so, okay? And then I can maybe draw the, we know where the mean is going to be, so we can do actually AB line. And the horizontal line we can put at k divided by 1 minus phi. This is the formula for the mean. Okay. Of course, any of you are generating different processes, but we see that we're generating persistent processes. You see, we're below the mean and we stay here for a long time. We're above the mean and we stay here for a long time. If you remember, we noticed this property when we took the seasonal difference of the log of the air passengers time series. It was very close to this behavior, if you remember. Okay. Okay, this has some more like local movements that the other one seems not to have. But I mean, it's amazing how I generated this by random, but they look pretty much the same. So this is one of the generations of my AR1 process with coefficient 0.9. And this is the air passengers after the log and the seasonal difference. They look similar, okay? This is what I wanted to show you. That's statistics. We build models that try to mimic the behavior of real data, and then we estimate what we're missing from the models, so the coefficients, the parameters, usually using like maximal likelihood and so on. Okay. Let's go back here. Support. So this would be very, for example, a very not very persistent process. Okay. You see, it tends to change sign almost every time. It's much more rough, and it's closer. It's not white noise. Still, we have some memory, but the memory is very short. Okay. Again, we can also look at the estimated autocorrelation function. So actually, in this case, I would expect some memory, but it's so small that I don't get it. Maybe I start with a slightly more persistent process. So it's somewhat more persistent, not strongly persistent, but in this case, we see there is some autocorrelation that goes to zero actually pretty quickly. Okay, but we see the pattern that I showed you. This is, of course, a sample autocorrelation function, so it's not the theoretical one. So there is some, of course, noise here. Okay, but it looks like the autocorrelation function of a AR1 process, because it goes to one in a geometric fast way. And then, of course, as I told you, as soon as I go closer and closer to the situation of a random walk, well, this is actually, yeah, for example, this looks like a non-stationary process. Because we have like this constant that kind of plays its role. Probably if I add up some observation, like if I simulated 1,000 observation, then I will notice that it goes back there. See it. There is also one reason. We are simulating processes that are not, that they don't have zero mean. Okay, the mean we see, if we put the k, we know that the mean depends on the k and on phi. Okay, so we see the mean is up here, but we are starting the process from zero, and of course, what happens is that the first observation is zero. Then the process goes slowly if we're in a very persistent process toward its mean, which is up here. But we let the process start from zero. That's why we always have this kind of ramp at the beginning. Zero would be a very, very rare observation in this process. So that's why it's kind of climbing up very slowly. Of course, it would be better looking if we let the process start from, for example, from the mean instead of a arbitrary point as zero. We can do that. For example, we can put init equal to, and we can put it equal to the, for example, the mean of the process. Now you don't have this ramp at the beginning. And that's why the process looked non-stationary. As I told you, this process is much more persistent, has a longer memory, because we are close to it's not random walk, but it's 0.98. So it's still stationary, but closer and closer to being non-stationary. So we have a longer mean, so longer persistent. This process is simpler to predict than the other ones that we predicted with a smaller phi, okay? And of course, if I put, well, let's put this now the mean equal to zero. If I put one here, of course, well, that goes to infinity. It's not nice, but so I just put zero here as well. And otherwise, this goes to infinity. So if I go like this is going to be a random walk. Okay. Actually, it's a random walk with drift. Why is that? There should be no drift here. Strange. Okay, it was just slow. My computer is very slow. So this is a random walk. Okay. And of course, in this case, the autocorrelation function is not defined, but the theoretical, the sample autocorrelation function we can still compute, and it's you see that it goes down linearly. It doesn't goes down in a geometric pattern. It goes down linearly. So you can notice if a process is integrated also by looking at the autocorrelation function. Of course, if we put a negative phi, stationary but negative, well, it doesn't matter. I put it equal to 0. Then you see a process that tends to change sign every time. Of course, it's a negative phi. So if yesterday was positive, today it's very highly probable that the value is negative. If yesterday was negative, it's very likely that today is positive. So it tends to change the sign very often. It may look in some way non-stationary invariance, but it's just an illusion. This looks like because it's persistent, and if there was a large jump in the last value, well, this jump is reversed by the phi equal 0.9 minus 0.9, so it's reversed to the other side, and it tends to jump up and down for a while, but it's not the effect of a higher variance because the variance is constant. It's just the effect of a persistent, negatively persistent or anti-persistent, maybe you can call it, process. Okay, because it just reverts the same value. If it's a high, it will be high on the other side and then back and so on. Okay, so this is but this is less common in well, maybe if you have like a electroencephalogram or something like that, maybe could look something like, in economic data, this would be very rare. Okay, but there are some medical processes that can look like this. Okay. And of course, we can now increase, this is just the AR1 process. So we played around with the AR1. We can generate very persistent, less persistent, in some way, anti-persistent processes. We can go up to unit roots and so have like non-stationary process. Okay, I didn't show you an explosive process. So let's take 1 point, very small number above 1, okay? Let's see what happens. Let's put the mean equal to 0 or the intercept equal to 0. Okay, this is very, maybe it's too small. Oh, it doesn't behave too badly. It should actually explode. Of course, it depends how far. Okay, here it explodes. But of course, it can explode in both directions. It depends. It's random. So maybe I generated again, as you see, it explodes in the other direction. Okay. So if it's above 1 or below -1, then you kind of get this kind of processes that can last only for a given period of time. Otherwise, they will be just out of range. Well, you see, if it's if it's explosive but only slightly, maybe it takes a longer time to see. But for example, if I make a much longer time series, you will see it, right? So sooner or later, it will go either to infinity or minus infinity, okay? So this could be a model for financial bubbles, for example. Okay, let's play around now maybe with AR2. We just play around with the AR1, the AR2. Of course, we will not play with AR3, 4, 4. Just because the AR2 can show you something more. I want to define you one more thing that we have to look at when we look at such processes, which is related to the autocorrelation function, and it's called the partial autocorrelation function. So what's the partial autocorrelation function? So we said the autocorrelation function is just between, for example, let's take gamma 2. So this is just the expectation of yt. Okay, let's take a mean zero process, so I write less things. Okay. So this is the autocorrelation function of a stationary process. The partial autocorrelation function is a correlation function that tries to control for the intermediate effect. For example, take an AR1 process. In an AR1 process, yt minus 2 is influencing yt minus 1, and yt minus 1 is influencing yt, okay? So if we are in a AR1 process, so if you take the equation, there is not a direct effect between t minus 2 and t minus 0, okay? But there is an indirect effect, of course, because we can, for example, write this as phi. Well, instead of yt minus 1, I can substitute the definition. Okay, so we see that actually in an AR1 process, of course, yep. In a AR1 process, it looks like a process where there's just an observation influencing the next one. But actually, it's not that way. And we saw it from the autocorrelation function. All the past is actually influencing the future. Of course, this is a small number between -1 and 1. So the higher the power, the smaller the effect, right? So the older is the observation, the smaller is the effect. But there is like an indirect effect of t minus 1 and t, right? Okay. And we recall that in the autocorrelation function, indeed. The partial autocorrelation function wants to see if there is only a direct effect between two lagged observations. So between yt and yt minus 2, yt minus 3, and so on. And so it's defined, something it's called alpha, as the covariance. This is the partial covariance, and then of course you can compute the partial correlation. It would be the correlation of yt minus the projection of yt on, in this case, yt minus 1, and yt minus, sorry, yt minus, right, this is it. Okay. So once I eliminate the effect on yt due to y times t minus 1, I want to measure the direct effect between yt and yt minus 1, because in this way I'm eliminating the transitory effect, the transient that goes from t minus 1 to t minus 2 to t minus 1, and then from t minus 1 to t. In this way, it's like I try to fix the intermediate effect of time t minus 1 on t to see if there is direct effect between yt and yt minus 2 in some way. Okay. Or if we can, I can try to make it more understandable. Suppose we have a sequence of observations. So in an AR1 process, we know there are only direct effects, okay? And so if I eliminate this direct effect and I compute the autocovariance between these two observations, well, this is 0. But if I have a AR2 process, there is a direct effect of the lagged one, but also of the lagged two of the variables. So in that case, I eliminate the direct effect, but not the indirect effect, but not the direct effect, okay? So the autocorrelation function is just trying to isolate the direct effect between yt minus k and yt, eliminating the transitional effect due to, for example, the fact that of an AR1, for example, influencing always the next value. And why do we need both the autocorrelation and the partial autocorrelation function? Actually, mathematically, the partial autocorrelation function is just a linear transformation of the autocorrelation function. So it's not very interesting. But it helps us to find out what kind of process generated the data. Okay. So, for example, let's go back to our well, sorry, I wrote H, but this is just the 2. Okay. So let's go back here. So we're simulating, for example, let's go back to a stationary process. In this case, very long. So this is the autocorrelation function. Of course, now we have a lot of observations. So the estimate is great. So it's very precise. It looks pretty much like the theoretical one. So the partial autocorrelation function, which you can obtain using PACF function. In this case, this is an autoregressive process of order 1. So there is just a direct effect of the last observation, but not of previous observation. So I expect the partial autocorrelation function to show there is just one leg that is different than 0 and all the other ones being 0. Whoops. And that's it. In this case, the partial autocorrelation function, again, for a reason that I don't know, instead start from 1. So the ACF function produces autocorrelation starting from 0, but the PACF function starts from 1. Okay. It's just the way it is. I don't know why they designed it this way, but keep it in mind. I'm not sure. I don't remember how Python does that. Anyway, just look at if the 0 is included or excluded. In this case, the 0 is excluded. So we have a very strong value for the first partial autocorrelation, and then all the other legs are 0. Okay? And that's correct, because the direct effect in an AR1 process is just of the previous observation, but not older than the previous observation, okay? So let's go to the AR2 and play around with the AR2. The AR2 can make also even more interesting paths. So, so we have like a phi 1. Let's start with 1.5 and phi 2. We can start with minus 0.7. For example, we can have the solution. So we know, is this process stationary? Okay, if I sum the two coefficients, I get a number which is below 1. So maybe it's stationary. But you can always use the polyroot function that wants the polynomial coefficients in this order. So in our case should be 1 minus phi 1 and then minus phi 2. So these are the solution, the roots of this equation. What do you see here? Well, they're not real, they're complex roots, okay? Okay, and you will see it, of course, if we have autoregressive process with real parameters, as we have, then if there are complex roots, they always come in conjugate pairs. So you have the same real part, and then you have plus and minus the same imaginary part, okay? Anyway, we're mostly interested in the modulus of this, so we can take the modulus, and we see that both roots in modulus are greater than 1, which means that we have a stationary process, okay? So we expect this process to oscillate around a fixed mean. If we don't have a k, the mean will be 0. If we have a k, the mean will depend on k and on the sum of phi 1 and phi 2. But anyway, we can use our filter. Again, we generate from normal, random white noise or random variables. No. And then the filter is going to be phi 1 and phi 2. And of course, the method will be the recursive. In this case, I'm simulating without a constant, so we can start simulating from 0, so because the mean is 0. Okay, maybe this is even too long. We can make it somewhat shorter. Oops. Okay, let's comment about this process or the sample path of a process. Of course, this is a sample path. You will generate a different ones, right? Okay, there is some persistence. And indeed, the sum of the coefficients phi 1 plus phi 2 is, I think, 0.8. So it's not extremely persistent, but it's persistent. And it kind of generates cycles. Of course, they are stochastic cycles. So some cycle is longer, some is shorter, the amplitude may change. But this is an AR2, and we saw that it's an AR2 with complex roots. If we get complex roots, as we have here, as I told you, we have like an oscillatory process, stochastic oscillatory process. So this could be a good model, for example, for, as I told you before, like a business cycle in economics. Goes up and down, not in a regular way. Otherwise, there is a famous time series, which is also in R. It's called sunspots. So it's the number of sunspots counted every year, starting from I think 700s and so on. So that's a physical time series, and it measures the solar activity. Sunspots are ways to determine how much solar activity there is, and that's we can look at that time series. It kind of look like something like this. It's got an average cycle of 11 years. So the sun has an activity that cycles over 11 years. And so this kind of model, for example, is good for the business cycle, but it's good also for sunspots. So there are many examples of things that kind of move this way, okay? And if I look at the ACF of this process, maybe let's simulate it longer because so we have a better estimate. So like 10,000 observations, it's going to be very long. Here. Okay, this was the process. Well, okay, now it's very long. We cannot recognize anything when it's so squeezed. But what we see here, so this is the autocorrelation function of an AR2 with complex roots. So the root that it goes to 0 at exponential rate is still good, is still valid, but it goes up and down because of the complex roots. As I told you, complex root means we see cycles, okay? And the cycles you see, of course, also in the autocorrelation function. And actually, you can also compute the kind of the average duration of the cycle by looking at the peak from peak. So peak from peak would be like here would be about 13 years, okay? So on the average, from peak to peak, it lasts 13 years. I told you that the sunspot was 11 years, so by changing slightly the numbers we use, probably match something close to the sunspot. But anyway, the numbers we will put in these models, we will estimate on data, okay? So we don't have to invent values for phi1, phi2 as we are doing now. There will be, of course, the parameters we want to fit on data. So the model will depend on these parameters, and these parameters will be fit on the data by usually either minimizing least squares or maximizing likelihoods, okay? How is the partial autocorrelation function? You can try to guess that. So what's the partial autocorrelation function? It's measuring only the direct effect between the present and the past. And in AR2, the direct effect is only the last observation, 2 observations ago, and then stop. So we expect the partial autocorrelation function to be different than 0 just for the first 2 lags, and then go to 0. Let's verify if that's true. And that's it. So first 2 are different than 0s, and the other one 0s. Okay. This is very close to the theoretical or the population autocorrelation or partial autocorrelation, because I simulated from 10,000 data. So it's almost, we have so many observations that the sample error is very small, okay? Of course, when we estimate those quantities on shorter time series, this will be much more noisy. So for example, if I take just 100 observations, which is more like a real sample, for example, if you have economic data, it still works, but you see, the noise is higher, and indeed the bands are also larger. Sometimes you also have some estimated autocorrelation that is larger than the coefficient, the confidence interval, which is 95% confidence interval. So 5% of them should go out, even if they are 0. Okay, but the first two ones are different than 0. Yeah.
So in general, the T-2 is positive because it's
one is positive. Yeah, one is positive.
So is this because of the side?
Well, it's because of the sign I gave to. So the first one has a positive sign, and the second one has a negative sign.
Oh.
Of course, you have to watch out. For example, if I choose the second to be minus 0.5, if you sum it up, you have unit roots. Actually, you have even 2 unit roots, and so you will have a non-stationary, an integrated process. So we have one root which is 1, and the other root is larger actually than 1. So the second root is stationary, but the first root is 1. So this is non-stationary, and you see it from here. This is more. Of course, we can compute those. This still holds, but this goes to 0 very slowly in some way. And you can play around with these numbers and you get Sometimes will be oscillatory, sometimes not. Of course, I could give you formulas to understand when, well, this is oscillatory, for example, so we have complex roots. You see here the cycles. So this is about 7-year cycles. Anyway, as I told you, this we don't have to pick the numbers here. We will estimate them on the data. So for example, let's take our air passengers time series. We saw that we need the log for stationarity in the variance, and then we have to take the seasonal difference to get rid of the seasonal non-stationarity, okay? So let's try to see how the AC, well, we can I don't know, call so D12 for seasonal difference, L for log, and air is the air passenger. So we want to take the difference of the log of air passengers, right? And the difference has to be a seasonal difference. So this is our time series. We can assume this is fairly stationary, okay? I recall that this is circa the yearly increment. So from 1 month to the next, the same months of the next year, it's the relative increment. So this 10 is 10%, this 0.2 is 20% as well. So we got also an interpretation of these numbers, okay? Okay, it doesn't look like a white noise, and we can verify that by looking at the autocorrelation function. And of course, we can look at also the partial autocorrelation function. Okay, so this is the autocorrelation function. It goes to 0. There is some range persist a little bit to stay negative here, but mostly it goes to 0 pretty quickly, right? What about the partial autocorrelation function? Well, the first lag is large, and the second is kind of large. Maybe it could be generated by an AR2. Then, of course, one thing to notice, the ones that wrote the ACF and the PACF function for R, if we pass an object time series, like the one we're passing, which is a monthly time series, instead of writing the lags here, they measure in years, okay? So 1 is 12 lags, is 1 year, okay? It's just how they wrote it. If you pass instead a vector, so not a time series, then you will read the lags here, okay? Indeed, we had just vectors before and we had the lags. Here we have the years, so 1 year is 12 lags, because it's a monthly time series. Just because they wrote it this way, so you can notice. But anyway, okay, a part of this, which is relatively large, but it doesn't have a very clear meaning because it's not even on the 12, it's later. But it looks like this time series could have been generated by an AR2 process, because we have the first two partial autocorrelation that are different than 0, and the autocorrelation function that goes gradually to 0. Okay, so this is basically how a time series analyst tries to identify, well, in this case, pure autoregressive models. Of course, we're still missing one part. We're missing the moving average part of the model. We will learn how to deal with them. But it's very like handcrafted. Of course, you can try to make everything automatic. In R, for example, there is a auto-ARIMA functions that try to do that. And of course, if you have thousands of time series, you have to make it automatic. You cannot analyze 1,000 time series. But if you have just to analyze and predict few time series, usually you beat, I would say almost always you beat the automatic algorithm. Okay? And auto-ARIMA is even not that good. But anyway, so this is basically how it works. Let's try to fit our first autoregressive model to this data. And I let you notice one thing. Do we need the intercept? I would say yes, we need an intercept, because even if this is stationary, it's not mean zero. The mean is here. I mean, zero is here, but the mean is somewhere here. Okay. So we need to estimate an AR2 process with intercept on the log and then difference, seasonal difference of the data. Okay, that could be a good model for this data. Is that all clear? So we came to this proposal, to this possible solution of the prediction of this time series, first considering the non-stationary part of the time series, which is actually the most important, and then the stationary part, which is important just for short-range prediction. As I told you before, a stationary process is a process that eventually forgets the past. Okay. So in the short run, the stationary part of the process that we are going to fit is important, but for long-range predictions, then the non-stationary part will prevail. Okay. So whatever you do with the data before applying, for example, an autoregressive or ARMA model, okay, that's more important. So the non-stationary treatment of the data, or the deterministic also part of the data, is much more important in long-range prediction than the stationary part. Anyway, let's try to fit all of this. I would use, there is an ARIMA function inside R, but for some reasons, maybe I can tell you later, or I never tell you, it's better to work with the ARIMA capital A, which you find in the forecast package, which is actually just a wrapper of the ARIMA function, which is in the base R, but it has some more features that make it more interesting. So I would say starting from now, let's always load the library forecast. Actually, the library forecast also have a capital A ACF, a capital P PACF functions. So for example, so this is a function of this library, which doesn't plot the zero. Okay, it looks just like the other ones, but it's not plotting the log zero. It starts from 1. And it's more coherent also with the PACF. And it doesn't use the seasonality. So you see the 12 here, and you don't see the year. And this is the partial. So it's just the same thing we saw before with a slight change. Okay, we see the logs and not the years, and we don't see the zero log in the autocorrelation function, which is very stupid to show. Okay, and they're just capitalized instead of them. Okay, the ARIMA function. So let's look at the help. So it follows actually, we don't know the AMA part yet. Okay, so we are going just to use the AR and the I. So I is for integrated process, AR is for autoregressive, and then later we will do the move and average part. So how does it work? First of all, we have to pass a one-time series. In this case, we pass the air passengers. Then we have the seasonal order and the non-seasonal order and the seasonal order. We haven't done yet, okay, we've done something about the seasonal. We just talked about the seasonal difference. Keep in mind that this is very standard. In all the literature, you will find out that ARIMA models are sorry. Are defined this way. So there's AR, and then there are the orders of the AR part. Non-seasonal and seasonal. There's integration here. So how many difference I have to take to make it stationary? The D, well, this is a D. I just, when I write vertical, I'm not very precise. So this is the number of non-seasonal differences, and this is the number of seasonal differences. And the NA part we have still to define, but the moving average part, this is the order of the non-seasonal part, and this is the order of the seasonal part. And this is the frequency of the observation, so the seasonal frequency of the data. So for monthly data will be 12, okay? So this is like universal. You will find in any book, in any articles, okay? And of course, all softwares are in Python, of course, as well. They use the same ordering, okay? So we have to pass the time series. In this case, air passengers is a time series object, so it's already got a frequency defined, which will be used. Okay. So air passengers is not a vector, is a TS object, so time series object. It's got the dating and it's got the frequency. So we don't need to specify the seasonal frequency because it gets it from here. You can also specify if you need it. They decided that you shouldn't know it, but I think by looking at the small a ARIMA, you can learn how it works. So if you want to define also the seasonal frequency, you have to pass a list with the order and also the period, so the frequency or the seasonal period, whatever you want to call it. That works also if you use the capital A ARIMA, okay? Anyway, let's go back there. So in our case, what we want to do is, first of all, take the log. Of course, we could take the log of the data and then fit the model. The problem is that, of course, when we ask the predict function to predict, the predict function doesn't know that we took the log, and so we would have to take the anti-transformation after predicting. Well, one good thing about the ARIMA with capital A is that there is a lambda, and the lambda is the lambda of the Box-Cox transform. So if you put 0 here, you get for free the logarithm, okay? You don't have to. And that, for example, the other ARIMA function, small a, doesn't have it, okay? So you have to manage the transformation, the Box-Cox transformation by yourself. In this case, it's all done. Then, well, one day I will tell you what this bias adjustment is, but not today because I already told you too many things. And so what we want to do here is, okay, take the log. So take the log lambda is equal to 0, right? Then we want to take a seasonal difference. What I have to write here to take a seasonal difference? What do you think? Huh?
Oh.
1 here. So this is PDQ. D is the number of difference. This is seasonal. So you have to put 1 here. Okay. Is that clear? So here would be a simple difference, and this is the seasonal difference. Okay, and then if I want to estimate an AR2 after having taken the seasonal difference, well, I didn't define the seasonal AR process, so you know what that is. But so for AR2, I just have to write here 2. Okay, so let's try to estimate this. Oops, I'll write the name of the parameter so it's maybe more readable. So we want AR2, we don't want any simple difference, and we don't want the MA part, which we don't know yet. As far as the seasonal order, we just want the seasonal difference, so 0, 1, 0, okay? And then we want the log. And for the log, we have to put lambda equals 0, okay? And then other interesting things are here. Okay, this is somewhat tricky. If we reason in terms of constant or intercept, constant and intercept are like just synonymous. It works exactly as I told you. Now, why is there also include mean or include drift? Let's reason about, let's take the AR1. Let's go back to the AR1. Here. So, now the AR1 with constant. Here. So, if we have a stationary process, the meaning of the intercept is that if I have a k which is not 0, so I have an intercept, then I have a mean which is not 0, right? And we compute it. It's the mean would be this number here, okay? But if phi or phi, whatever, is equal to 1, we have a random walk with drift. So the mean of k is actually the mean of the increment, because if you take this on the other side, you have the increment, this is 0 mean, and so the mean is k. So the intercept, if we're modeling the time series without any difference, is just the mean of the data. If we're working on the first difference, the intercept becomes actually like a slope, a mean slope, like in the random walk with drift. Okay, so that's why they did this kind of chaos here. So include means it's so interpreted. In case they don't put any difference, put a mean, and by the default is true. And that would be include constant true. So if you write include constant true, that overrides whatever. Okay. So this prevails on these two here. If you put one difference, then the mean becomes a drift. Okay. So in that case, if you put a difference here or a difference here, it doesn't matter. Include mean doesn't really matter. So it would look at the drift. And if you put two differences, then it doesn't use anything, because after two differences, usually you don't have any fixed mean. But anyway, include constant instead, work on whatever the difference they are. Okay. So if there is no difference, the drift there is not a constant that is not 0 will make a mean which is not 0. If we took a difference, a constant which is equal to true will give a drift, so a linear trend in the data. Okay, this is not clear, or is it clear? It's not clear. So if it's a stationary process, the constant is proportional to the mean. If it's an integrated process, then the constant is proportional to a drift, so like a linear trend. Because the mean of an increment is like a linear trend, a positive or negative way. Okay? So I usually use the include constant and ignore all the rest. In this case, I would write include. Why do I want to include the constant? Because we saw that mean increments, or because we took the seasonal difference was larger than 0. So I need actually, indeed, this is a growing time series. And after I take the seasonal difference, the mean, of course, is not 0. Otherwise, you wouldn't be growing, okay? And that's it, okay? Of course, I can add regressors. So we can do many things, but for the moment, just start with this model. What I did wrong. I just changed the order, but that doesn't really matter.
Order is not written well.
Ah, okay, thank you. Okay, thank you. So the solution, it's always easier than when you look for the type of error. Anyway, so let's see what's got printed if we just print the output of the model. Okay, time series is air passengers. You see the Arriva model written in the standard form, as in whatever book you will read. So 200010 with seasonality 12. With drift, why a drift? Because there's a difference in the constant, and this produces a drift. Okay, we just said box transformation, yes, with lambda equal to 0. So we estimated it. This is phi 1 and this is phi 2. And this is the constant. Okay. And of course, they're estimated by maximum likelihood. So we also have standard errors. We could test if they're significant, of course. If this is larger than 2 times the standard deviation, it's significant at 95%. Okay. Or with size 5%, whatever you want to call it. Okay. So all these parameters, they're significantly different than 0. And this is an estimate of the sigma square, so the variance of the white noise. Of course, is very small because we're working in logs, and of course the variance is going to be very small. And then we have the log likelihood, and probably you all know this information criteria. This is the Akaike, this is the corrected Akaike, and this is the Bayesian information criteria. They're used to compare models with different parameterizations, okay? So usually you want to pick the one that minimizes all this information criteria, okay? What about the prediction? We can do it with the predict, or we can also use the forecast, which is of the forecast package. We just have to pass the mod, and I think we just need to say how many steps ahead. Maybe, I don't know, we want to predict 1 year. And these are the... So by default, it produces... it's called point forecast, which would be assuming Gaussianity, it would be the conditional expectation, but actually it's not the conditional expectation because we're working on the log and then take the back transformation. So the bias adjust is bounded to this concept. We will see it maybe later. And then we get some prediction intervals. So like these are like 80% by default and 90% prediction interval. I think it's got also some automatic plotting function, if I well remember. Yeah. So the forecast package has many convenient things, much more than basic R. For example, the time series is actually contained in the model object, so that's why he's able to print all the original data, because they are contained in the model. If you look at the model object that I created, the ARIMA object, the data are inside there, and that is able, of course, to produce prediction and also the confidence interval for the well, prediction intervals, actually. Okay, they're not confidence intervals, they're prediction intervals. You know the difference between the confidence interval in this case and the prediction interval? So the confidence interval would be the uncertainty about the mean of the process. So when you're predicting the future, usually use the conditional mean. Of course, that's not the real conditional mean because you estimated the coefficients. Now the phi1, phi2, and the variance of the white noise, they're all estimated. They're estimated on data, so they're uncertain. We saw the standard error of those numbers. And so this, of course, translates into an uncertainty of the future mean, so the conditional mean of the future observations, right? And so a confidence interval would be a confidence interval for the future mean of the time series. A prediction interval instead is some way to describe the future distribution of future data. If you take the mean, that's just the conditional mean of the data, but it's a random process. So the future may have many different paths, and of course these paths are described by the distribution. Okay, and here, for example, it's designing the 80% central part of the distribution and the 90% central part of the distribution around the mean. Okay. So a prediction interval is the distribution of the future observation. And if I read, for example, the 80% prediction interval, what's that? It means that in 80% of my prediction, the real future data will be between in these bands, and in 20% of the times will be outside of this band. Okay, so that's how it's. So there are pretty different things. So the confidence intervals and the prediction intervals. And these are prediction intervals, okay? Of course, I could have faked, I didn't know the last year, I didn't do that, okay. The nice thing about this function is that, as you mentioned, it's predicting the original data. So actually, there are ARMA models, or the autoregressive model we built was a model to predict the 1 year increments, actually 1 year relative increment, because it's a log, okay? But then this function, this forecast function alone, will take the exponent, will seasonally integrate the prediction and then take the exponential. So otherwise, all these things we had to do by hand, and it's good that we have there. So this would be the first exercise in doing an autoregressive, purely autoregressive model. We'll do more exercises. Of course, this is a simple time series. We will analyze more complex time series with multiple seasonalities. So we will have to find out ways to mix seasonalities, maybe every 7 days, every 24 hours, every year. So we have to build a lot on these basic tools that I'm presenting to you. But it's already a very powerful starting point, okay? And yeah, well, then we will see also tests to see if data have a unit root or not. So if I have to take a difference before working with data, even though I'm not a great fan of this or unit root tests, especially if the time series have many complex seasonalities. But anyway, we'll talk about it. Any questions? I know I gave you a lot of information. So kind of overloaded. It's also Friday, so sorry about that. So if there are no questions, also from home or whatever you are, we can stop here and we'll see each other on Monday.